to the cloud. Okay, so today is lecture number 7, I believe. Number 7. And let's look at this pointing vector a little bit like in detail, in depth. So we see that all these terms in this formula are described by products of two different quantities. For example, pointing vector, right? Pointing vector is the cross product of electric field and magnetic field. So it's a product of two quantities. The power is equal to the product of electric field and current density. Okay, and also, for example, the energy of the electric field is given by epsilon naught E squared over 2. So it's the product of electric field by electric field. And likewise, the energy for of the magnetic field is given by mu naught magnetic field squared over 2. So it's a product of magnetic field by itself. And all these equations, they describe the energy, right, in the system, either conversion of energy, like this Joule formula here. So it's conversion of energy into dissipation, for example, or generation energy due to some energy generator. These formulas describe the energy density in a system. This pointing vector describes the energy flux, energy flow from point to point, okay, like in form of electromagnetic field. And we often interested in the time average of the product of these two, I mean, of the complex functions, right? So this electric field, currents, magnetic fields, as we discussed, we can write them in a complex form. Like, for example, let's derive a formula in a general case. So let's consider, for example, a quantity A, which is a function of time, and we write this quantity in the complex form of this form, right? A tilde e to the power of I omega t, where a tilde is a complex number which gets the amplitude of the quantity I naught times e to the power of I phi a. So it's a phase. Okay, so this a tilde, this complex amplitude describes the real amplitude and the phase of the quantity. And we consider to have another quantity b, which is again complex, b tilde e omega t. Okay, and we working in the complex terms and writing the quantities like in this form, in this complex form, we always have to remember that the actual physical quantity is the real part of the quantity, right? So we have to write the real part real part, for example, real part of A and real part of B. And now let us derive a formula for defining the time average of a product of two quantities, A and B. So I write real part of A times real part of B. So what it is? So you remember that if you have a complex number with real part and the imaginary part of this complex number, the real part of the number or any function can be found by taking the sum of the number plus the complex conjugated version of the number and divide by 2. So it's a general way of defining the real part of any complex number or complex function. So for the first one, I write 1/2. So this is this half here. And then I take real part, which is a tilde e to the power of I omega t plus the quantity itself plus the conjugated version. So a tilde complex conjugation e to the power of I omega t. Okay, and times the second one. So 1/2 of b tilde e to the power of I omega t plus b conjugated e to the power of minus I omega t. Okay, so let us expand. The parentheses. We got 1/4 here. Then I have 4 terms: a times b tilde complex conjugation without exponential function, because e to the power of I omega t times I to the power of minus I omega t cancel out. Okay, and I have another one like this, but complex conjugated. So it's a conjugated b. This is the first part, which is fully real. And then the second one, a tilde b tilde e to the power of 2 I omega t plus a tilde conjugated b tilde conjugated e to the power of minus 2 I omega t. Okay, so 2 parts. One doesn't depend on time, and the second one, so here we have no dependence on time, and the second part does depend on time, but at twice larger frequency. And so usually, especially when the frequency is large, but in any case, if you average some quantity over time, you expect to get a quantity that doesn't depend on time, right? And in fact, if you average up this e to the power of 2I omega t over time, with time period, you'll get 0, because this is essentially sine and cosine, and averaging sine or cosine over one period of the field is equal to 0. Okay, so anyway, this part is vanishing after the averaging, and I write for the average, so mean value or average value of the product of real part of the A and real part of B. So it's average over time is equal to 1/4 A tilde B tilde conjugated plus, and let me write A tilde B tilde conjugated. Okay. Why? Because this reminds me this formula for the real part of any quantity. If I multiply by 2 and divide by 2 both parts, I mean the numerator and denominator, this part is exactly the real part of A tilde B tilde complex conjugated. Okay, and I end by this simple formula 1/2 real part of A tilde B tilde conjugated. Okay, so let me run down this as a final formula. Real part of A times real part of B time average is equal to 1/2 real part of A tilde B tilde conjugated. Okay, so if you're interested in time average value of any product of two quantities that depend on one frequency, so it's harmonic functions, A and B are harmonic functions. Harmonic functions, you can represent them in the complex form using this real part of A tilde times e to the power of I omega t. Okay, and after these calculations, we came to this simple formula. So you need to take 1/2, and then the real part of the product of A tilde and B tilde complex conjugated. Right. For example, for the active part of the power that we discussed last week, or the absorbed or radiated part of the power, right? So what it was P active. The power is the product of the current and voltage, right? And if we're interested in the active part, so we take the time average of this, and we came to the simple formula 1/2 real part of U times I, voltage times current. Okay. Or, for example, in this Poynting vector, let's say we have the electric field, right? Electric field density. So for the electric field density, we have this formula epsilon 0 E squared over 2. Okay, so now applying this formula, so what my A and B now is E, so just electric field, because now I have electric field times electric field. So for the time average of the energy density of electric field, now I have what? Epsilon naught over 2, and then the time average of the electric field squared, which is over 2, 1/2 real part of E times E conjugated, right? E times E conjugated, and of course tildes. So E times E conjugated is exactly the absolute value. And the absolute value is it's real number, so no need to take the real part. So what we get epsilon naught over 4 and the E modulus squared. Okay, so electric field modulus squared is it defines the energy. Okay, so yeah, so it's a useful formula, and today we actually will use it. when we will discuss the plane wave, which is the part of the next and the final part about introduction to Maxwell equations, which is essentially the application of Maxwell equations to electromagnetic field. Okay, so the point number 13, I believe. This one was 12. Yeah, 12. So now it's 13. Let's say, or let's formulate this in a way like electromagnetic field can exist without charges. Okay, so electromagnetic field can exist without charges and currents. That's interesting because electric field only or magnetic field only cannot exist without charges and currents, because charges and currents, they are the sources of electric or magnetic field. In contrast, electromagnetic field can exist without the charges, right? And it exists in the form of electromagnetic field. So let us derive this fact again from the Maxwell equations. So we write the Maxwell equations. The first one was rho over epsilon 0, rho c. C stands for the conducting charges. Okay, so the second was the divergence of magnetic field is 0 because no magnetic charges. The next one is curl of electric field. It was equal to minus dB over dt. Okay, and the last one was curl of magnetic field. So in our case, it was curl of H, and then it was the time derivative of electric field on the right side. But let me multiply both parts by mu 0, and mu 0 by H is equal to B, right? In this case, in the free space. So mu 0 times H is B, and now it's the right hand side is equal to mu 0 times epsilon 0 dE over dt, and plus the current of the free charges. So as we said, we assume now that our system has no charges. So this guy and this current equal to 0. Okay. We have no charges in the system. We have no charges in the system. Let me take now the curl of electric field. So I take the curl of this equation. So curl of electric field. Okay. So what it is? It is equal to the curl of the right side. So it's minus curl of dB over dt. Again, the time derivative and special derivative can be exchanged. Change the order, so it's equal to minus then d over dt, and then curl of b. Pretty good. Curl of b. But now, I mean, we know this formula for the curl b, right? And we can plug in this formula here. and it's gonna be time derivative of the right side of the formula. So it's gonna be minus mu 0 epsilon 0 d2e over d2 over dt2. So it's a second order time derivative of electric field, and the current is 0. Okay. So next, for this one, we had a formula in one of the first lectures. We derived we probably derived this formula. So it was it was the gradient of the divergence, right? So the curl times of some vector, right, is equal to the gradient of the divergence of the field minus Laplacian or nabla squared A, okay, or Laplacian A. So in this case, we have the field A, the field E, electric field. So we're gonna get the gradient of divergence of E minus Laplacian E, and it's equal to minus mu 0 epsilon 0 d2E over dt2. Okay, so now I look at this formula, at this part, and I notice that without charges, the divergence of electric field is equal to 0. So this part vanishes, it vanishes, and I get the result, basically, which is the Laplacian of electric field is equal to mu 0 epsilon 0 d2e over dt2, right? So it is exactly the wave equation. Wave equation, if we take an assumption that 1 over the velocity of this field or of this wave, and by velocity of this wave, this electromagnetic wave, we usually denote it by c, right? So the c squared, yeah, it's gonna be c squared, and it's equal to mu 0 epsilon 0. Okay, so if we take an assumption that the product of mu 0 epsilon 0 is equal to 1 over the velocity squared, then this equation is written in this form: 1 over c squared d2 e over dt2. Okay, so this is exactly the wave equation. From this formula, I can derive the formula for c. So it's going to be 1 over square root of epsilon 0 mu 0. Okay. So for the first time, this formula has been derived by Maxwell, and Maxwell calculated the number, I mean, for this velocity, and find out that it coincides with the velocity of light, and he made a prediction that light is an electromagnetic field. And after that, other scientists like Gertz and others, they measured the velocity of electromagnetic field and find out that it's equal to, I mean, the same number, the speed of light. So this c is known as the speed of light in free space. So speed of light in free space. 3 times 10 to the power of 8 meters per second, approximately, right? And yeah, so we derive this formula for the electric field, and of course, if you start from the formula for the magnetic field, you take the curl of it, then you can plug in this curl of electric field to the formula, and you will come to exactly the same equation for the magnetic field. The nabla of magnetic field is equal to 1 over c squared d2b over dt2. Okay, so and I also remind you that the nabla, or sorry, the Laplacian is nothing but the nabla squared, and it's given by the sum of the partial derivative of second order by x, y by z. Pretty good. Okay, so now, so this is 13. Let us let us split into two parts. So yeah, so it's going to be 13.1, a subsection 13.1, plane waves. Plane waves. Okay. So let us consider a wave described by these wave equations. Okay. Let us consider a wave propagating in the direction of z axis, along z axis. So plane wave. Consider wave. Consider wave propagating along z axis. So what it means, the wave propagating along the axis, it means that the field, for example, electric field, depends on z and doesn't depend on x and y. Right, so we have dE over dz n equal to 0, but dE over x, dE over dy is equal to 0. Okay, and the same for the magnetic field. It also depends on the z coordinate and no dependence on x and y. Okay, so let us derive the properties of this field from the Maxwell equations. So we return back to the Maxwell equation. The curl of electric field is equal to minus dB over dt, right? So for the curl of electric field, it's a vector, and it's equal to I, the unit vector in the x direction, right? D over dy e z minus d over dz ey plus j, so it's a d z e x minus d over dx e z plus k. It's gonna be d over dx e y minus d over dy e x. Okay, and it's equal to the time derivative of the magnetic field. So now, let me, yeah, and by the way, we have the second equation for the curl of the magnetic field, right? So the curl of magnetic field is equal to epsilon 0 d E over dt. So this is the second one. And for this one, I basically have exactly the same equation for the curl up to substitution E by H. Okay. So now, since my electric and magnetic field depend only on Z, I can cross out, depending on Z, yeah, I can cross out this one, and both of these. Okay, so I get the equation for the curl of electric field, which is minus I d E y over d z plus j d e x over d z, and it's gonna be equal to minus dB over dt. Okay, this is the first one. And for the curl of magnetic field, I basically have exactly the same, minus I d h over y, or dhy over dz plus j vector dx over dz is equal to epsilon 0 d over dt. Okay. So this is true for a field of any polarization, of any orientation. We now assume that we have fixed the orientation of electric field to be directed along axis x. Okay, so let me draw it schematically like this. So I assume that this is x, this is y, this is z. The field propagates along z, and the electric field is polarized along x. So this is my E here, okay? So electric field has only component EX, 0, 0. Okay? So the EX component, so the field is polarized along X, but this EX component is a function of Z, all right? So after fixing this polarization, I can now cross out this term here, okay? And from this first equation, I get the following. So I got J times dEx over dz equal to minus dB over dz. Yeah, so I see that the time, it's a t, sorry, it's t. Here, it's a t, of course. So the time derivative of magnetic field is parallel to the axis y, right? So this j is points along the axis y. So the magnetic field is parallel to the axis y. So it's orthogonal to electric field. This is first interesting and important observation, that magnetic field in the plane wave is orthogonal to the electric field. Okay. Another observation, since pointing vector, which is equal to the cross product of electric field and magnetic field vectors, right? So it's supposed to be orthogonal to both of them, electric field and magnetic field. So the pointing vector points in the direction of wave propagation. So this is the pointing vector direction. Okay. Yeah, and this also means that in our case, the component, so we have component by, right? So by ion zero, it oscillates along y, but bx is equal to 0, and also hx is also equal to 0. So I will get the second equation. From this second equation, we get the second one, which is minus I dhy over dz is equal to epsilon naught dE over dt. Okay, so now it's much simpler. Let's return to this picture. So now we have the case of electromagnetic field which propagates along axis z. Electric field is polarized along x. Magnetic field is polarized orthogonal to E, so it's along axis y. And yeah, and this type of field is known as the plane wave. So it's a plane wave. Plane wave, well, because it depends on only one coordinate along which it propagates. That's why plane wave. For example, the radiation from antennas, the radiation from antennas in at some distance, or a distance sufficiently far from the source, from the antenna, is well described by plane wave. Also, radiation from a laser, like light of a laser, also in a good approximation is a plane wave. Okay, so the plane wave. And so far we didn't imply any particular special dependence on time, okay? But we can assume that our fields are harmonic functions of time. So oscillate at one single frequency omega, okay? So for harmonic functions or fields, we can write the general solutions for electric fields. In our case, it's polarized along x. It gets the amplitude, okay, index 0, times cosine kz minus omega t, and plus some phase phi. And for the magnetic field, we have polarization along y, the amplitude y0, cosine kz minus omega t plus angle phi. Let me make a quick gap with a break. All right. So yeah, so this is the general solution to these wave equations. Do you have any questions thus far, by the way?
Yes, Professor. I have one question.
Uh-huh. Yeah, please go ahead.
Hello. We are trying
Yes.
to like to check that we have electromagnetic field without charges and without current, right?
Yes. Mhm.
And we substitute zero in the Maxwell equations for the charges and current. And at last, we got those results. Is that means like we have electric field, the last result we get, and magnetic field. Like I cannot understand practically, and I cannot see it here.
Yeah, so first of all, don't confuse this J with current, okay? So this is the unitary vector in the axis Y. So this is not current. This is, I mean, I guess for this reason, usually people, instead of J, they write, for example, Y tilde, something like this, to denote the vector along Y. But we use this J, and typically it doesn't give any, I mean, any problem. So that's not current, that's a unitary vector along Y. This is first. Second, these two equations, in our case of the plane wave solution, so first of all, it denotes solution is a solution to Maxwell equation, and we just derived this from Maxwell equations. From the Maxwell equations without sources, without charges, without currents, right? From these Maxwell equations. Okay, and these solutions to the Maxwell equations, they simply state that in every point, for example, I consider, for example, the first one. In every point, if magnetic field in this point depends on time, for example, oscillates or whatever, just depends on time, this dependence on time of magnetic field causes the change of the electric field, but special part of the electric field, right? So that this is the special derivative of electric field. So the time derivative of any field describes how the field changes from one instant to another instant. Okay, so if it changes, then this change of magnetic field causes the change of electric field in space, which means change of the field from one point to another very close point in space. Okay, so change of field of magnetic field in time causes changing of electric field in space. And likewise, in the second formula, the change of the change of electric field in time causes the change of magnetic field in space, and the two are they form a a connected equations, right? This is the system of two equations. You can read it like from this term here, the change of electric field causes the change of electric field in time causes change of magnetic field in space, and then change of magnetic field in time causes the change of electric field in space. So these two fields, they connected in time and space through these two equations. And we have no charges, no currents here. Okay, and now we consider the harmonic version of these fields. Harmonic is the field that depends on one single frequency. So it's over here, one single frequency, here and here. And we plug in these two formulas to our Maxwell equations. But before doing that, let us look at this phase of the cosine function. Okay, so this cosine k z minus omega t plus phi, right? So this is known as phase. So this is phase of a wave. So this phase depends on the coordinate and depends on time. And this phase, this cosine function is a periodic function of 2 pi. Okay, so this phase is repeated in space and in time every 2 pi instance or 2 pi distances. Okay. And let me take the time derivative of this phase. The time derivative of phase. The time derivative of phase itself is 0. Okay. So, and the time derivative of the left part is let me write step by step. So the time derivative of kz minus omega t plus phi is equal to time derivative of phase. It's equal to 0 because the phase doesn't change when I change the time. Okay, and now I take the time derivative of each component in the phase. So the k, the wave vector doesn't depend on time. The z does because the wave propagates in space. So it's basically the time derivative of z. Z defines the coordinate of the wave front. Okay, the wave, it has front. The front propagates through the space, and this dz over dt defines the velocity of the propagation of the front of the wave in space. So this is the velocity. So this is velocity. And what is the velocity in our case? It is c, right? The speed of light. Okay, so then the second term is minus, let me change the color, minus omega. dt over dt is equal to 1. And the initial phase is also constant, so it's also the time derivative is equal to 0. So this one is equal to 0. So I substitute c for dz over dt, and I get k times c equal to omega, and hence I get formula for the k, which is equal to omega over c, right? So this omega over c, the k, is known as the wave number. So it's a wave number. Wave number, and it plays the same role as a omega, as a frequency, because if you look at this cosine kz minus omega t, right? So we have two variables here, z and t. If I fix z and change t, the omega here defines the period of this function when I change in time. Okay, so it's basically defines the how fast the field changes or oscillates in time. Likewise, if I fix time but vary z, this k, this wave number, defines how fast the field changes in space. Okay, so I change the z, cosine is a harmonic function, so this k defines the rate of change, the function, this harmonic function in space. And this wave number plays the role of the frequency, but for the special variable. Okay, wave number. So now, as I promised, I plug in these equations to the Maxwell equations, in our case, this plane wave, and I get what? Let me see. So for the dE over dZ, I get dE over dZ. I get EX0. Cosine turns into minus sine kz minus omega t plus phi, right? Times it was z, so times k is equal to minus dB over dt. So it's a minus dB. B is mu 0 h, right? So it's a dh over dt. So it's a hy0 sine plus kz minus omega t plus phi. And the derivative of minus omega t is minus omega. Okay. So what I get, I can cross out the sine function here. Minus and minus also cancel out. And I get a pretty important result that the amplitude of electric field in a plane wave times k, the wave number, is equal to mu 0 omega h y0. Okay, so now I substitute the k, which is omega over c, to this formula, and then I can cancel down the frequency in both of parts. Yeah, so I get the electric field amplitude over c is equal to mu 0 h y0. Okay. So here I can, for example, find the electric field amplitude, which is equal to c mu 0 h amplitude. We can frame this formula. We can also substitute c by 1 over square root of epsilon 0 mu 0, right? And this gives us, so what it will be, mu0 over square root of epsilon 0 mu0 cancel down, and I get mu0 over epsilon 0, right? Something like this. So it's gonna be ex0 equal to square root of mu0 over epsilon 0 hy 0. We can also frame this one, this formula. So we notice that the ratio of the amplitude of electric field and amplitude of magnetic field, right, is equal to this constant mu0 over epsilon 0 square root. And this quantity is known as the wave impedance, or free space wave impedance, and denoted by Z sub 0. Okay, the wave impedance of free space. So since this Z0 is a constant, it's defined by mu0 and epsilon 0, which are constants, and the square root. So we can calculate the number, and in fact it's equal to about, or approximately, 377 ohm. Okay, so this is something that one can remember. So in the plane wave, electric field and magnetic field amplitudes, they connected through the value of the wave impedance of the plane wave, and they are basically, so this formula states that in the electric field amplitude is 377 times larger than the amplitude of magnetic field. Okay, but this is for the international system of units. If you remember from the first lecture, we stated that we will work in the international system of units, this SI system of units. In other systems of units, for example, in this SGS system, the electric field and magnetic field, they have equal amplitudes. In our system of units, they connected through the wave impedance of the free space. Okay, so for example, when we will have calculate the interaction of plane wave with some objects, like numerically calculate or simulate such problems, we will see that the electric field is 377 times stronger than magnetic field. Do you have any questions so far? And from this formula, by the way, we also conclude that if I substitute the H field by B field, right, I get another, I mean, it's basically the same formula, but in other terms, that electric field over magnetic field is equal to the speed of light. Okay, so if my magnetic field is represented in terms of B field, then electric field over B field is equal to C. Okay. So let us maybe write a summary for the plane waves, because this part is kind of important. So the summary. For the summary, in plane wave, first, in plane wave, electric field and magnetic field are orthogonal. In plane wave, wave. Electric field is always orthogonal to magnetic field. Okay, so second, the amplitudes of electric and magnetic field, they connected through the impedance of free space. So electric field amplitude over magnetic field amplitude is equal to Z naught, or electric field over B field is equal to C. Okay. So the third one is the direction, right? The direction is given by direction. I mean, the propagation direction is given by the Poynting vector, which is E cross H. E cross H. It's orthogonal to both electric field and magnetic field. Okay, and it's also instructive to define this wave propagation by promoting the wave number to the vector. Okay, so this wave number, which is omega over c. Okay, we can promote it to the vector k vector, which is k times the amplitude times the direction. Okay, so this, for the plane wave, this k vector, which is known as wave vector, coincide with the direction of the Poynting vector in the free space. Another important observation is that the phase of electric field coincide with the phase of magnetic field. Okay, so in the plane wave, the phase of electric field and magnetic field coincide, and this is important function, as we will see shortly. The fact that the phases of electric and magnetic field equal allows to wave propagate in free space. If you, for example, could control the phase of magnetic field versus electric field, you would control the amount of energy that propagates from freely propagating wave up to the localized and standing wave, not propagating field. We will see that shortly. Okay, and maybe the last statement about intensity. Okay, so intensity is something that we, of course, use much more frequently than Poynting vector. Poynting vector is I mean, it's a nice quantity for calculations, but in the lab we don't use Poynting vector. We use the concept of intensity. Intensity is the function that defines a quantity that defines the power or energy flux per unit area per time. So intensity is equal to energy per unit time is a power. So I write power per unit area. Okay. Or the flux of Poynting vector per unit area. So this is the intensity. So by definition, intensity is given by the time average of the Poynting vector over the period. Okay, so this is the definition of any function depending on time. And today, in the beginning of this lecture, we derived this formula for any function, for the mean value of any function depending on time, function of any quantity that is the product of two functions of time. So it's going to be 1/2 real part of, in this case, it is the E field cross magnetic field conjugated, right? Okay, so in the case of plane wave, magnetic field and electric field connected through this wave impedance. So magnetic field is equal to electric field over impedance. And we come to the conclusion that the intensity in this case in the case of plane wave is equal to 1/2 e to the power of 2 over z naught. Okay, so this is the intensity of a plane wave. Like, for example, if in the lab you have a laser, you can define or measure the intensity of the laser. And after the measuring the laser intensity, you can, for example, calculate this electric field of the laser field. Okay, and the electric field then can be used for many things. Yeah. So let us consider this average of the pointing vector in somewhat closely, somewhat in more detail. So as we discussed, the time average of the plane wave, of the pointing vector is given by 1/2 of the real part of the product of electric field and magnetic field star conjugated. Okay. So now I want to consider the case that is more general, comparing to this result above, which is fair for the plane wave. Now I assume that the electric and magnetic field, they can have different phase. Okay, so for example, for electric field, I can write something like this: the amplitude of the field times the e to the power of I omega t plus phi. Okay, so this is the field depending on time, and it gets this phi. Let's put e here. So this is the phase of electric field. Okay, and the same for the magnetic field. We've got the amplitude times the exponential function I omega t plus phi h, the phase of the magnetic field. Okay, and now I go ahead and substitute these two to the formula above. Okay, and get the next result. So it's for the time average of the pointing vector, I get 1/2 the real part of of the electric field is E0 vector e to the power of I omega t plus phi e. And the cross product. So let me let me write it like this. So I write E amplitude cross H amplitude. Okay, and then after that I take this exponential function e to the power of omega t plus phi e times the second one, which is complex conjugation. So it's going to be minus e omega t plus phi h. Okay, yeah, pretty good. So it's equal to, the amplitudes are real, so I can take them out from the from taking this real part of. So it's gonna be e cross h. Okay, and then goes real part of e to the power of I omega t minus I omega t cancel out. And I get this e to the power of I e phi e minus phi h. Okay, so the phase difference of the electric and magnetic field. So we can consider now a couple of several cases. So the first one, if phase of electric field is equal to phase of magnetic field. So no phase difference between the electric and magnetic field. Okay, so in this case, the exponential function turns into 1, real part of 1 is 1. So we get for the time average of the Poynting vector is the result that we had above, right? 1/2 of the electric field times magnetic field amplitudes. Okay, and this is the real valued quantity. Okay, so the energy is also the Poynting vector is real valued because the phase difference between electric and magnetic field is 0, and this makes the field propagates freely in the, for example, in free space, and this wave carries the energy in space. Yeah, so it's a propagating field. But what if I can change the phase difference between electric and magnetic field somehow, and I make the phase electric field and magnetic field difference to be equal to pi over 2. So what would I have in this case? So in this case, this guy, this exponential function is equal to I to the power of pi over 2. And I use Euler's formula, right? Cosine pi over 2 plus I sine pi over 2. Okay, so cosine pi over 2 is equal to 0. Sine pi over 2 is equal to 1. So the result is imaginary unit. And the real part of imaginary unit is, of course, 0, because the imaginary unit is purely imaginary. Okay, so in this case, I came to the conclusion that the time average of the Poynting vector of the field, of electromagnetic field, in which electric and magnetic field oscillate out of phase, this phase difference pi over 2, we call this in quadrature. So the fields oscillate in quadrature. In this case, the Poynting vector over average over time is equal to 0 because real part is 0. Okay, so what it means? It simply means that the field doesn't propagate anywhere. So no energy propagation. So no energy transfer. Electric field is there, magnetic field is there, the fields have energy, the energy oscillate, etc. But the energy doesn't propagate anywhere. It stays locally, stays somewhere. This is interesting. This is interesting result, which simply says that we can not only transfer energy using electromagnetic field, we can also store energy in the electromagnetic field and keep it somewhere, just changing the phase between electric and magnetic field. Okay, and of course we should, for completeness, we can also say that in general case, when the phase difference neither 0 nor pi over 2, right, we would have the Poynting vector average over time written as E cross H star, right? It will get two contributions: the real part and the imaginary part. So Poynting vector is also real, gets also real part and imaginary part. And if you take the real part of this formula, you of course get this real component of the time average Poynting vector, which describes the energy transfer. But taking the imaginary part, you can take the you will get the imaginary component of Poynting vector that describes the reactive part of the Poynting vector when energy stays somewhere in form of some circulations, etc., without real transfer. And now you might be curious, like how we can store this electromagnetic energy without propagating, right? Without transfer the energy. And of course, the answer is the standing wave in resonator modes. And this is the next part I want to tell you about. So this is the second subsection in this 13th item, or so 13th point: standing waves. And resonator modes. It's pretty important. I mean, we already discussed once this case of microwave oven, right? Microwave oven is a metallic box. The generator, this magnetron, right? Magnetron generates the electromagnetic fields inside the microwave oven, and of course, these fields, they don't propagate anywhere. Why? Because they exist in there in this metallic box. And why they don't propagate anywhere? Because electric and magnetic field have the phase difference of pi over 2, roughly pi over 2. those of you who like aware of the properties of, for example, metals, we will discuss this briefly, hopefully next time. But metals have no magnetic properties like these metals used in the microwave ovens. They have no magnetic properties. For magnetic field, the microwave oven is like nothing, like empty space, free space. So magnetic field or magnetic component of this electromagnetic field doesn't feel the existence of this microwave oven metallic box. But electric field does. Electric field does. Electric field, of course, reflects from the walls of this metallic box. And this reflection gives this pi over 2 phase difference between electric and magnetic field. Okay. And exactly because of this phase difference, the field doesn't propagate anywhere from out from this box. So let us maybe consider this in a little bit more detail because of its importance. So let me draw two mirrors. So this is the mirror 1. This is the mirror 2. Okay. And I introduce the coordinate system. Like this one is Z. This one is X. And this one is Y. Okay. And I write down the, so by the way, I assume that the length of this, the space between the mirrors is equal to L capital. Okay, and what I need else, that's it. So, and yeah, so these two mirrors, so these walls are mirrors. So a mirror here I assume to be perfect. It means that magnetic field, as I said, doesn't feel the presence of these mirrors, but electric field perfectly bounce off the mirrors, totally reflecting from it. For example, for the leftmost mirror, the field on the left side, electric field, is equal to 0. It doesn't propagate, doesn't penetrate inside or through this mirror. For this reason, the electric field must have the 0 here at this wall. But the same true for the second wall. So the electric field also gets 0 on the second wall too. So it doesn't propagate through. And the field, electric field between these mirrors can exist only in form of a standing field like this, right? So yeah, sorry for my drawing, but yeah, so this is the point. The electric field, so this is electric field, gets 0 on both walls. Okay, and magnetic field, of course, also exists between these mirrors and oscillate somehow, and we're gonna define the magnetic field from this assumption. So for the electric field, I can write it in this form. So it of course depends on Z and time, okay, and it gets the amplitude E0. It's polarized along X by assumption. It depends on time as a harmonic function, so it's a cosine omega t, okay? But what about the special distribution of the field? So at Z0, it's equal to 0. Hence, what what function describes this behavior? The sign, right? So sign 0 is equal to 0. So I write it times sign some k, which is wave number to be defined for this case, times z. Okay, so sign equal of 0 is equal to 0. So this way I define this leftmost boundary, this point of my field. And what about the rightmost part, this second boundary? Okay, so the field also must be equal to 0 there. So sign of k times L also equal to 0. So I conclude that k times L is equal to what? Is equal to 2 pi times n, right? N is integer number. 0, 1, 2, 3, etc. And starts from n. So it's 1, 2, 3, etc. And in these cases, the sign is equal to 0, and the field is perfectly equal to 0 at the second boundary, at the second mirror. So I can substitute for k this omega over c, okay? So and divide both parts by L, and multiply by c both parts to get omega. And the omega gonna be equal to 2 pi over times c over L and times n. So this formula depends on the n. So I put this n here, okay? And this result indicates that the field in this between these two mirrors can be of specific frequency. Okay, so not all frequencies can exist between these two mirrors. Only those that equal to this omega 1 equal to pi times c over L, which is so-called fundamental resonance or fundamental mode. Fundamental mode or fundamental resonance or cutoff frequency. You can also say cutoff frequency. So this is basically frequency below which no modes, no resonances, no field can exist between these two mirrors. Why so? That's simply because for the field to exist, it must have at least half of the wave here, right? Because it must be end at both boundaries, so it must have at least half of the wavelengths. So it cannot be something like I don't know, something like this or something. Yeah, so it must be 0 here, 0 here. So it's a half of the wave. This omega depends on L, right? So if you make this L, for example, smaller, the frequency grows, okay? And for a fixed frequency, you always can find a distance between two mirrors when the field at this frequency cannot exist between two boundaries. Okay, so it's a fundamental mode, fundamental resonance, or cutoff frequency. And only those frequencies that defined by this formula can exist between two mirrors. Okay, so it's a you can say it's a quantization. So it's the field in the resonator becomes quantized. In fact, like if you know, or if you had a course on quantum mechanics, you know that if you put a particle between two mirrors, you get the same result. The energy becomes quantized. So this also relates to that. So the frequency becomes quantized, and but what is the magnetic field? Yeah, magnetic field is yet to be derived from Maxwell equations. Okay, so we use this curl of electric field, just minus b over dB over dt. Again, I remind you that the curl of electric field, or I remind you the procedure of writing down this curl. So it's we start from x, so this unit vector along x times the next one is y, so d over dy, then component z, so x, y, z, minus, I replace the z and the y, dz ey, plus j d over dz ex minus d over dx ez plus okay d over dx ey minus d over dy ex. Okay, so in our case the electric field has only dependence on z, so on z, so this guy is 0, 0, 0, 0, only two terms, but also the field is assumed to be polarized along x, so we have only one component of this. Sorry, not this one, the x component, so this one, not 0. Right, so d ex over dz, okay, is equal to what? So for electric field, we have this equation here, and we derive this one by z. So we have only one term that depends on z, is sine kz. So I write the part that doesn't depend on z. So it's E0 cosine omega t. Derivative of sine by z is cosine kz times k. Okay. On the other hand, this curl is equal to the minus time derivative of b. So minus dB over dt, okay, is equal to so it's y component, so it's y here, dB y over dt is equal to E0 k cosine omega t cosine kz. But this is the time derivative, and we need to multiply both parts by minus and integrate over time by arbitrary dimension. Yeah, so it's gonna be by equal to minus the integral the integration over time, so let's take everything that doesn't depend on time out from the integral. So it's gonna be E0 k cosine k z. The integral over of cosine omega t dt and the integral of cosine, of course, is simple. It's gonna be minus sine. No, it's just sine. The k cosine k z sine omega t times 1 over omega. Let me see. So the integral of the derivative of sine is cosine. So it's gonna be plus here, right? Yeah, it's gonna be plus here. Yeah. So yeah, so basically this is the answer. Yeah, now let us also use the fact that k is equal to omega over c to get rid of this omega here. So by is equal to E0 over c. This is exactly the result for the plane wave. Okay, so the wave impedance in the free space and wave impedance in the resonator is the same. So the electric field and magnetic field, they connected through the wave impedance or through the speed of light in terms of, in the case of B vector. Cosine k z sine omega t. Okay. So interesting result here is that magnetic field depends on time as a function of sine omega t. Electric field depends on time as a function of cosine omega t. Okay. So indeed, we've got this result that magnetic field and electric field, they shifted in phase by a factor of pi over 2. So electric and magnetic fields have this difference, the phase difference of pi over 2. And this is exactly what makes the field not propagating anywhere. So for example, if we calculate the Poynting vector, which is E cross H, okay, we would get what? Let's consider only the time dependent part. So it's going to be cosine omega t times sine omega t. Cosine omega t times sine omega t, and then if you if you average this Poynting vector over the time, you would get what? You would get 0 because the integral over the period of cosine t times sine t is equal to 0. These functions are orthogonal. The functions are orthogonal, and the integral is equal to 0. So the energy doesn't propagate. So like let's say no energy flux. No energy flux. The energy stays between these two mirrors. It's trapped in the system. So a system like this is called a resonator. Why? Because the field stays in the system. It oscillates there. The wave travels back and forth from one mirror to another mirror, bounces off, and most importantly is that why it's resonator? Because it resonates. Why? Because only specific frequencies are allowed to exist in this system, in this resonator. Only these frequencies, only field that has the frequency defined by this formula is allowed to exist in the resonator. Okay, and the resonator is one of the most important thing in electrical engineering, let's say. So any radio, when you tune radio, you tune this omega to specific frequency that selects the carry signal, the carry frequency, right, from the spectrum. Otherwise you would get like a very noisy signal. So the radio selection, also lasers have resonators, and the resonator of a laser makes these systems, these lasers, to be so coherent. Okay, to radiate only one specific frequency or one specific color. For example, you have this laser pointer, like red laser pointer. Why it's only red? Exactly because it gets the resonator that allows only the red color to exist, to emit, etc. Many applications of resonators. And as we discussed, no energy flux. The real part of the pointing vector is zero, and zero the time average of the pointing vector. But what about the energy, right? So flux is zero, but what is the energy? Energy, for example, electric field energy is given by epsilon 0 over 2 electric field squared. And again, considering only the let's actually plug in the whole formula. So epsilon 0 over 2. And for the electric field, we have E0 squared. Okay. Then sine squared kz times cosine squared omega t. So for the energy, we've got, instead of product of cosine and sine, we have cosine squared. And this is important because the time average of sine cosine is equal to 0, but the time average of cosine squared is equal to 1/2. Okay, so the energy averaged over time, we got epsilon 0 over 2 E0 squared sine k z. Okay, and the same for the magnetic field. We can, even without these calculations, these trivial calculations, for the magnetic field average over time, we get mu 0 over 2 h0 squared sine squared kz, right? So the electric field I in 0, it depends only on the coordinate. I mean, the time average energy doesn't depend on time. It depends only on the coordinate, both electric and magnetic fields. And also, here, actually more important fact is before this averaging. So average is good, but let us look at this formula here. So the energy depends on time as a cosine squared omega t, right? And now if I find the energy of the magnetic field, I will get omega 0 over 2. Oops, sorry, it's mu 0 over 2 h0 squared. And then what I had is E0 squared over C squared cosine squared kz times sine squared omega t. So this is something what I wanted to emphasize. So electric field depends on time as a cosine squared omega t. Magnetic field depends on time as a sine squared omega t. Of course, I could start from sine functions, and then I would get for electric field is sine here, and for the magnetic cosine. It doesn't really matter. What matters is the phase difference of the electric and magnetic field energies. Okay, so electric field, so the energy of let's actually write this down like this: electric field energy and magnetic field energy oscillate out of phase. Oscillate out of phase. And this phase difference of the energies is equal to pi over 2. Which means that the energy converts inside this resonator. Energy converts from electric energy into magnetic energy and back, right? And this is exactly equivalent to what we have, for example, in the case of the RLC circuit, right? So from a simple analysis of electric of the RLC circuit, we will quickly discuss these circuits hopefully next time. In short, the circuit of capacitor and inductor, where capacitor stores the electric energy, inductor stores the magnetic energy, and the electromagnetic field in such a circuit can exist only when the electric and magnetic field or electric and magnetic energy converts one into another, like electric fields converts to the magnetic field and back, because the phase delay between electric and magnetic field in the capacitor and inductor have the phase difference of pi over 2. Okay, so this is also the air resonator. Okay, which is a pretty good point. All right, so this is this is all I wanted to discuss today. Let me stop recording and then we can discuss the